Thank you, Cidinha. Thank you for this very nice introduction. So kind. Thank you. I'd like, can you hear me? Sorry.
Yes, yes, sure.
So I also, I'd like to thank the organizers for this invitation. So it's my great pleasure to give a talk here. Let me start. My plan is to talk about old results in Lipschitz equivalence of functions, and also about new results. Unfortunately, the new ones are not my results, but I'm also happy to talk about it. I talk about old result was proved with Professor Maria Ruas, and in the complex case, and in the real case was they were proved in a joint work with Levi Brahi and Daniel Panassolo. And the new results that I'm talking about in this topic is proved by Leonardo Câmara and Maria Ruas, and also by this is in the complex case. In the real case is a recent thesis of my former PhD student, Sérgio Álvares. Okay. So let me start. In this very beginning of the talk, I will talk about equivalence of function germs in R or C. Okay. K for me means R or C, the real numbers or complex numbers. So suppose you have two germs of functions defined in Kn. You say they are equivalent if you have a change of coordinates in Kn, such that you change of f to the function g in this way here. Let me. Okay. G composed to the change of coordinates is equal to f. It means geometrically the following. Here, this is the domain of f. You have the special fiber of f equal to 0, and you foliate the plane, the germ of the plane. You foliate with the generic fibers f equal to c, and you have the same for g. Have the special fiber of g equal to 0, the 0 set of g, and also you have a foliation of the germ of the plane by the generic fibers of g. So my map phi is a map from here to here, such that phi sends the level of set, the level C of set, the level C of the function f to the level set C of the function g. Okay. This level set goes to this level set. In particular, the special fiber goes to the special fiber. Okay. So we see of kind of analytic equivalence you have when you change the regularity of phi. Okay. If phi is bi-analytic, I mean, is when phi is a diffeomorphism, analytic with its inverse also analytic, we call this equivalence analytic equivalence. When phi is a Lipschitz map and its inverse is also a Lipschitz map, it's the case of we call bi-Lipschitz, when phi is bi-Lipschitz, we say this equivalence is a Lipschitz equivalence. When phi is a homeomorphism, is a continuous function, and its inverse is also a continuous function, we say this equivalence is a topological equivalence. Of course, if two function germs are analytically equivalent, so they are bi-Lipschitz equivalent. And if the two functions are bi-Lipschitz equivalent, they are topological equivalent. And you don't have, in general, the other way around doesn't work. Né? Sometimes you have two functions which are topological equivalent, but they do not Lipschitz equivalent, and you have functions which are Lipschitz equivalent, and they do not analytic equivalent. So let me talk about the finiteness theorem in this context. This set means the set of polynomials in two variables. This is polynomials. Two variables. And degree D, okay? This is the degree of the. So in this case, this set, you can write down in this way, A, X, D, A, 0, D, plus A1, D minus 1, X, D minus 1, Y, plus A, I, J, X, J, Y. You can see this set as some Kn, okay? The set of polynomials of degree D in two variables. The coefficients are in C or R, doesn't matter. So, and you consider all the polynomials in this set as a function germs at the origin, okay? They are polynomials, then you can see set polynomials as a function germs. And you consider the analytic equivalence. And you ask by the equivalence class of these function germs. Whitney showed that if you are looking for a kind of classification of this set up to analytic equivalence, you have some trouble because the number of classes, you have infinite many uncountable of classes of equivalence if you consider analytic equivalence. Maybe we can do the classification. Some people succeeded to classify some analytic equivalence. For instance, Abraham Refez and Marcelo Fernandes, and also Maria Lendice. But it's not easy. It's not an easy task to do it. If you look for the equivalence class up to topological equivalence, let me fix just polynomials in two variables. Now you have finite many classes. Doesn't mean that you have an easy task, but maybe you have this kind of result. Say that you can have discrete invariant to describe all the classes of a result. And what about the Lipschitz equivalence? What about Lipschitz equivalence? It was proved by Henri Parushinsky that you have a kind of problem like we had in the considering analytic finite many uncountable classes if you consider such a set up to Lipschitz equivalence. So today I plan to talk about this equivalence here. And my point is, how far this equivalence relation is from the analytic one. Okay. So we have Lipschitz equivalence implies topological equivalence. The topological equivalence is between Lipschitz equivalence and analytic one. So by this kind of results mentioned here, the number of classes, the equivalence classes, it gives us a feeling that the Lipschitz equivalence is closer than analytic equivalence. They looks like analytic equivalence in some sense, okay? The Lipschitz equivalence is far from topological equivalence. This is the feeling, but we are not sure. So let me talk about the Henri Parushinsky invariant. They build an invariant to show this preview result here. This is a kind of a cross ratio. Cross ratio was used by Whitney to show this result. And Henri Parushinsky created a kind of cross ratio, but it's not cross ratio. This far, not cross ratio for sure. So suppose you have a two variable function germs in C2, and the zero set of this function is not tangent to the vertical line. We have coordinates here, x and y. And suppose the zero set is not tangent to the vertical, okay? Something like that. And take a Newton-Puiseux parameterization of the branch, of a branch. This polar set here, this is important. We take the polar set df dx equal to 0. This is associated to this hypothesis here. Maybe you have more than one branch. You take one of them, take a Newton-Puiseux parametrization, and you take the development of this function here. You compose this parametrization of this branch, okay? Here we are writing x as a function of y, okay? Then you put the parametrization of the branch here as a graph, né? And you compose this with f. You take the development, the Taylor development of that, and you have an initial part of this development. C0 is different to 0. This is a coefficient. C0 is a point in C star, and we have a power here. This power is a rational number, positive number, and associated to this branch, we have two numbers. One of them is in C star, and the other one is in Q plus. Okay, and you put this number here. You separate this monomial for any branch parameterization of branch of the polar set, polar curve. Okay, and you divide this by C star, looking for or considering a C star action on this set. This action is given by multiplication on this variable. Okay, so this set is equivalent to you change y by a multiplication by C star number. Change y by lambda times y. Then here you have lambda, something like that. Okay, they are equivalent for us, and you divide this by this equivalence relation. This is our invariant. This is the invariant defined by Henri Parushinsky. So let me take an example here. And the polar set here, the polar curve. I have this. The polar curve. We have two branches. This is one branch. This is another one. Yeah. Maybe we change. Yeah, I don't know. So you compute the development of this guy. When you compute this, you have x3 y6 plus y6 minus 3 times 3 times t square t y, wow, t y6. This is equal to 1 minus 2 t cube. Okay, and you compute now f along this branch. This give us this invariant. So our invariant is this set 1 minus 1 plus up to the C star action. Okay, so you will see that for if your parameter is small enough, okay, small enough, ft is Lipschitz equivalent to fs, and then t cube is equal to s cube. Then you have moduli for the Lipschitz equivalence just using this invariant of Parushinsky, this one. So this is a way. It's kind of recent result. We have 20 years, and before that, people working Lipschitz geometry was thinking that there is no moduli for the Lipschitz equivalence of functions. So most of the result was to show that how can you show that two functions are Lipschitz equivalent? And in the end of the day, the only machine you had to prove that was by integrating vector field. So most of the result was to find vector field that conjugate vector field that build a flow, a Lipschitz flow that conjugate two functions. Oh, was here. So let me put this machine of vector field in a definition. Suppose you have two function germs which can be embedded in a family. It means that f of t0 is equal to f and ft1 is equal to g. Okay, and f is a family of function germs. We say f is strongly Lipschitz equivalent to g if there exists a vector field, a family of vector field, is one parameter vector field, such that this is a special, this is special, the vertical component of the vector field does not degenerate, but to have more properties. This vector field is Lipschitz in the variable x, Lipschitz. And this vector field, these equations means this vector field is tangent to the fibers of the function f. And you have more properties. This vector field preserves the tx. Then, if there exists a vector field satisfying such a properties, we say f is strongly Lipschitz equivalent to G. Okay. In this case, the family is called strongly Lipschitz trivial. This is the machine I mentioned before. If two functions are strongly Lipschitz equivalent, then they are Lipschitz equivalent. Let me show what is happening geometrically. Here we have our function. This is the function f. This the special fiber of f. This is a generic fiber of f. In the bottom, we have a description of the function g. This is the special fiber of g. Then you have the generic fibers of g. Okay, and you ask for a family. We embed f and g in a family. You consider a tx. A tx t. Here we are in k. And we put f and g in a family. So when you do this, this is the generic fiber of the family f equal to c. And then this is the special fiber of the family. O equal to 0. So this, this means our vector field is tangent to the fibers of the family, this equation. Then our vector field is tangent to the fibers, all the fibers, the special and the generic fibers, tangent to the fibers. This equation means that our vector field preserves the tx. This is 0, this is 0. Then along this x, our vector field is vertical. And our vector field is Lipschitz. Then when you integrate the flow of V, our vector field, we have a family of homeomorphisms. The hypothesis that the T component, the vertical component of V, do not degenerate, give us when you take the integral curve of x starting in the bottom, this integral curve goes to the top. Okay. Once we are tangent to the fibers, this flow send the special fiber to the special fiber to the C level set of G to the C level set of F. They preserve the fibers. Okay. This flow is Lipschitz because the vector field is Lipschitz, and this homomorphism given by the flow send the origin to the origin, because our vector field is the vertical one along this axis. Okay, and our flow goes in this way. Then we have a bi-Lipschitz homomorphism between a neighborhood of this, the domain of G, to the neighborhood of the domain of F, sending the level set C of G to the level set, the C level set of F. Then this is a way to show two functions are Lipschitz equivalent. But we don't know if two functions are Lipschitz equivalent. This is the only way to prove you can build a bi-Lipschitz homomorphism between them. Maybe this is in a work by Citinha in camera, but I don't know. We are looking for some result like that, but we didn't succeed. So in order to see how far our Lipschitz equivalence is from the analytical one, you start to investigate such a problem with Professor Maria Ruas, and you arrive in these results. Suppose you have a family of two variables function, two complex variable functions, which are weighted homogeneous. We were inspired in the example of Parushinsky, but not homogeneous. I mean, we are weighted homogeneous with respect to the weights W1 and W2, and W1 is different to W2. Here we put W1 larger than W2. This is important. We are weighted homogeneous, but not homogeneous. And all the members of this, all the elements of this family are weighted homogeneous of the same degree. And suppose they are isolated singularities at the origin. So if this family is strongly Lipschitz trivial in that sense, the existence of such a vector field like I mentioned before, then all the elements of the family are analytical Lipschitz equivalent. So the existence of a Lipschitz vector field in the family give us any two elements of the family are analytically equivalent. This points out that the Lipschitz equivalence is somehow close to analytic equivalence. Analytic equivalence. It was proved in 2013. After that, such a result was improved by Leonardo Câmara and Professor Maria Ruas. This is not in 2003. This is last year. They proved the following. The setup is the same. We are in a family of weighted homogeneous polynomials with the same degree, weighted homogeneous but not homogeneous, with the same degree, and with an isolated singularity at the origin. If the family is a Henri Parushinsky invariant, constant Henri Parushinsky invariant, I mean, this continuous family has the Henri Parushinsky invariant constant. So the invariant of Henri Parushinsky does not change along the family. If you suppose that, then both ft1 and ft2 are analytically equivalent for any t1 and t2 in the domain of the parameter. Okay, this is a enormous improvement of our theorem before with Maria Ruas, because this is in the direction of if F and G are bi-Lipschitz equivalent, then F and G are analytically equivalent. But they do not prove this yet. This is they are close to get such a result. This is what we have in the complex case up so far. As far as I know, maybe this is the best result, two variable complex case. So what happens in the real case? Henri Paris used the same invariant, and they proved that this family is also this family also give us a moduli for the Lipschitz equivalence of real function germs. They use the same invariant. They compute the expansion of f along the branch of the polar set and consider such an equivalence. They divide it by C plus, I don't remember if it's C plus or sorry, R plus or R minus. And the invariant give us that in this family, F is not Lipschitz equivalent, Fs is not Lipschitz equivalent to Ft if S is different to T and they are positive. When S and T are negative, all the members of the family are bi-Lipschitz equivalent. In this case, we don't have polar set. In this case, it's easy to build a vector field and to show that all the members of the family are strongly bi-Lipschitz equivalent when T is negative. Okay, so then in 2008, I started to investigate with Lev Bibrahi and Daniel Panassolo how far the Lipschitz equivalence in the real case is from the analytic one. So then we consider weighted homogeneous functions, weighted homogeneous but not homogeneous. Let me define this set. This set is a triangle, is a holded triangle. In the play set here. The triangle with some contact here. It's not a geometric triangle. Okay, a topological triangle. And you consider functions with the domain is this triangle. Weighted homogeneous functions, whose the domain is this triangle. Okay. Our motivation was, if you have a weighted homogeneous like that. Then we start to investigation. This was our motivation. Okay. So, and associate to this function in this domain, take a height function. This height function is the restriction of our function to the level y equal to 1. This is one global function defining the interval 0, 1. This is the interval. And you associate it to our initial weighted homogeneous function, consider this height function. what we prove? We prove the following. If you have two real polynomials, which are weighted homogeneous but not homogeneous, with the same degree, and their zero logs are the boundary of this whole triangle, then they are semi-algebraically Lipschitz equivalent. If you don't leave, the respective height functions are analytically equivalent, up to a multiplication by a positive constant. This gives us somehow our Lipschitz equivalence is close to the analytic equivalence. So at least up to a kind of desingularization. Lipschitz equivalence of weighted homogeneous functions give us some analytic equivalence of the functions up to a desingularization. These height functions are somehow a desingularization of the function, the weighted homogeneous function. So, but let me put here. Here, we succeeded to find such a result just on this whole triangle. This is a severe restriction. It's not easy to. It was not easy for us to glue all the information we get in such a result for the pieces of this partition. We did not succeed to do this glue, and we finish. We stopped to investigation in this result. We are looking for a result like that. Koik and Parushinsky, in the real case, prove in 2013 if two real weighted homogeneous polynomials are C1 equivalent as function germs on the equivalent. Our goal was to prove that if such a function germs are Lipschitz equivalent as a function germs on this guy, then they are analytically equivalent. But it was too much for us. Then after that, I proposed to a student of mine to extend our result in the whole triangle to the whole plane. Then he defined more than one height function. Consider a real homogeneous polynomial, weighted homogeneous. So associated to this weighted homogeneous, take the right height function, the restriction of our function to this line, and take the left height function of f, the restriction of our function to this line, y equal to -1. Then you have two height functions. One is restricted to the line y equal to 1, and the other one is restricted to the line y equal to -1. Then let me put this definition. Let me remark that our height function here are functions from R to R. The result before the height function were functions from 0, 1 to R. Here, the domain is all the line, the real line. Okay. So, two polynomial functions defining, they are polynomial functions, they are defined on the real line, whole real line. Two polynomial functions are analytically conjugated, we denote this way, if there exists C, a positive real number, and a bianalytic diffeomorphism from R to R, such that 8 tilde composed to the bi-analytic map is equal to 8 up to a multiplication by a positive number. This is our conjugate, analytic conjugate. Then my former PhD student proved this result. Suppose we have two weighted homogeneous polynomials, weighted but not homogeneous, W1 is larger than W2, such that their zero locus intersect the half planes x larger than 0 and x smaller than 0. The left half plane in the right half plane. If f and g are semi-algebraically Lipschitz equivalent as function germs on the whole plane, then either the right height function of f is analytically conjugated to the height the right height function of g, and this means the left one is equivalent to the left one, or the right height function of f is conjugated to the left height function of g, and the left height function of f is equivalent to the right. It depends on the conjugation of f and g. If the conjugation of f and g send the right side to the left side, then we have this equivalence here. And if our map conjugated f and g send the right side to the right side and the left side to the left side, then you have this condition here. Okay. Then our moduli is given by two functions from R to R up to analytic conjugation of this function. Okay, so I don't know, I have time. So
yes, you have at least 5 minutes.
I have time. I plan to give an idea how to prove this result here.
Sure.
So the complex case. So I mentioned this result. This is the older one. Who have a family of weighted homogeneous functions which are not homogeneous, and with an isolated singularity at the origin. If this family is strongly Lipschitz trivial, then any two elements of the family are analytically equivalent. Let me show an idea how to prove it. Okay, this is the definition of weighted homogeneous polynomials. We are not in the case of two variables, it is the case of n variables. Let me denotate this set, the space of weighted homogeneous polynomials in n variables of degree d. This is a kind of Cn. This is a finite dimensional space. So if you have a family of functions in that space, all of them are weighted homogeneous. This is a kind of path in some Cn or some manifold. Okay, the space of weighted homogeneous of degree d is a finite dimensional space. Then how can you show that? How can you guarantee this path all the elements of this path are analyzed the lemma in a special way. Actually, this is a consequence of the mother lemma. To show that some path in a manifold is included in a G orbit of, you have a Lie group, and you have an action of this Lie group on this manifold, and this is in such a way that all the orbits are smooth, particularly when this Lie group is algebraic, all the orbits are smooth. Then you have the orbits of this action. The lemma mother is in the setup that you some up to some hypothesis, you can guarantee this path is included in only one orbit of this action. Okay, so our Lie group is a truncated of a group of diffeomorphisms, finally diffeomorphisms. So put here, this guy is included in a jet space. Our Lie group, you take the group of diffeomorphisms of Cn, the germs of diffeomorphism of Cn, and you truncate all the diffeomorphs, and you have a group. This is a finite dimensional group, and our set is including these manifolds. In order to show that two elements of these sets are analytically equivalent, we have to show that all we have to show that the two elements are, this action is given by that. You compose your function with a change of coordinate, and you truncate by this operator here. You take the m-jet of this compose. This is the m-jet of the diffeomorphs, acts on this m-jet of F by that, by this composition here. Okay, then the mother theorem says the following: if you have an arc and you are looking for a way to prove that this arc is only one orbit, then you have to prove that for all the points of the arc, the dimension of the orbit in this point do not depend of the point. So this is the first step of our proof. If you are weighted homogeneous and with isolated singularity, the dimension of this orbit can be computed in this way. The dimension of this orbit is equal to the dimension of the space minus the codimension of the orbit. Then if you prove that the codimension of the orbit is constant, you prove the dimension of the orbit is constant. So the dimension of the space, this space, is a m-jet space. Then this is the maximal idea of the ON, and you truncate by the power m minus m plus 1 of this maximal idea. And the dimension of the orbit, you have this space here. This space is this one. Is this one. The ideal generated by the zy times the partial derivative of the family with respect to zj. This is the tangent space. This is the tangent space of the orbit, truncated by this power of the maximal idea. Then using algebra, you show this dimension is equal to this dimension. But we know this dimension is equal to the number of variable plus the middle number of f. And since we are weighted homogeneous, this middle number depends only of the weighted and the degree of f. So this middle number does not depend on f. Okay? Then all the orbits have the same dimension along a path of isolated singularity weighted homogeneous function. So then we have the derivative of the path. The derivative of the path, the velocity of the path belongs to the tangent space of the orbit in the point. This is by hypothesis of our proposition. The derivative belongs to the tangent space of the orbit. This is the tangent space of the orbit for all the points along the path. This is our hypothesis. And the dimension of this guy does not depend of the point T. This is exactly what the mother lemma say to guarantee that all the path is in the single G orbit. This is a way to prove any 2 points in the path are analytically equivalent. This is proposition A. Let me come back to the hypothesis of the proposition A. This is the derivative of the path, the velocity of the path. We suppose is in the ideal, the tangent space with respect to the R equivalence. And this is enough for fixed T. If you are not in the weighted homogeneous case, this is not enough to show that all the elements are in the same orbit. But as we show, when we are in the weighted homogeneous case, the dimension of the orbits does not depend of the germ. Then you can use other lemma. In proposition B, now we use our specific case.
Alexandre,
Oh,
we have more few minutes, okay?
okay, I finish. So now we are in the case where you have 2 variables when weighted homogeneous, and suppose you are strong in bi-Lipschitz trivial. I mean, we are supposed the existence of such a vector field that trivialize this family. Then there exists K such that this guy is identically null along the polar set. If you have that, it means that the velocity of the path is a multiple of the y in the f dy plus a multiple of the dfy if this polar set is reduced. In the case of where this set is not reduced, we have more technical difficulties, but somehow is this. Then if you prove this proposition, this is a multiple of dfy plus a multiple of dfx, then this guy belongs to the tangent space of the R equivalency for the 2 variable sets. Okay. Then by proposition A, all the members of the family are analytically equivalent. Then it's enough to prove this proposition. And you prove this proposition this way. You have this vector field that trivializes F. This guy is Lipschitz. This guy is Lipschitz. Using this vector field that is tangent to the fibers of F, you can write this guy here in this way along the polar set. Because df is equal to 0, you don't have this component. Then this is equal to 0, this is minus here. Okay? Then this quotient here is a Lipschitz function. But this quotient is weighted homogeneous, and this quotient is a Lipschitz function. Then we describe our polar set using just roots. In this way, we intersect our polar set with a line, y equal to 1, and you take roots of this equation, are roots. For each root of this equation, you take the weighted homogeneous action, then you have parametrization of our polar sets. Sorry. Let me finish. Then this is a root, this is a parametrization. This is action. This is a root of this equation. You take this action, this weighted homogeneous action, you have a parametrization of the polar. They are the curves. And now we are computing this quotient along our polar set. We saw this quotient as Lipschitz. The claim is all these functions here do not depend on this index, the roots. This vector field, this component of this vector field is Lipschitz along the as Lipschitz. And this is weighted homogeneous along our polar set. Then this is S times the point in the one level Y. You just use this guy as weighted homogeneous of degree W2. Then you can write this guy in this way. From another way, this guy is Lipschitz, lambda Lipschitz. Then you see this size here is smaller than lambda times this. This is distance between this branch to this branch. So we have this guy here is smaller than this guy. Here we use that the W1 is larger than W2. Then this goes to 0 faster than this. This is why ky should be equal to kj. Then all this function here does not depend on y. Then they are only way. We have only way to write all these functions, k of t. Then we have our proposition. The difference of this guy, of this function, using this k function, is equal to 0 along the polar set. Then, using proposition A, you finish our proof. Okay, I finish here my mathematics talks. I ask one more minute to speak about a few words of gratitude. Okay? My math talk is stopped here. Let me say some words. So this is for the organizers. I'm so grateful to this organization that I need to say some words. Since long time, the Brazilian Mathematics Colloquium has been a place of inspiration for young people interested in mathematics in Brazil. In particular, the Singularidades section has contributed to this inspiration as a traditional part of this great meeting. For instance, I remember that as an undergraduate student in mathematics, I visited IMPA during one of the colloquium editions, and I attended my first planned lectures. It was given by Robin Hartshaw. I also remember that I attended a lecture by Professor Cidinha in the Singularities and Topology section. I remember this lecture of Cidinha and the lecture of Derek Hackle. It was a great time for sure. So this is why I would like to thank the organizers for give us this singularity session this time. We see this pandemic period has brought enormous difficulties for everyone, whether personally or professionally. It is a matter of fact, everyone is in trouble with this pandemic. Despite of these difficulties, Professor Miriam Manuel, Professor Marcelo Hernandes, Professor Aurélio Menegon showed their commitment, mainly with the young generation of people interested on singularity theory. Thank you very much for giving us this great section. Kindly, I ask everyone to turn on microphones and clap hands for the organizers. Thank you, guys.